Hello, everyone. I'm going to be doing my presentation today on density functional theory. So what is density functional theory? It's a computational approach to modeling molecules using functionals. And functionals are really just functions of other functions. Um, DFT methods are often used in computational chemistry, physics, materials science, anytime you need to model molecules or interactions between molecules on a pretty low level, with maybe hundreds to low 10,000s of atoms. Um, Functionals are based on the quantum chemical equation of or concept of the Hamiltonian, which gives you the energy of an electron in a certain state. So it's an adaptation of the Hamiltonian, which the DFT theory is based off of. Okay, so some background. DFT methods are based on something called electron charge density. There's this other type of method called con-sham methods, which you don't really need to know what that is, but it's just a hybrid between DFT and Hartree-Fock. And Hartree-Fock are kind of what you would think of as your first principles based methods. So those are going to be the more precise, but also slower methods for modeling. And con-sham take advantage of both the pros of these two types of methods. And so currently DFT and DFT hybrid methods are among the most popular methods used in computational chemistry because they have a really nice balance between calculating things quickly and calculating things accurately. And there's hundreds and hundreds of variations of these methods out there. DFT and DFT hybrid are kind of the parent umbrella terms that describe a whole field of methods. And so there's a whole bunch of different software packages as well that implement DFT and DFT hybrid. I've listed some that you might recognize. I personally use Gaussian and CASTEP the most, but it just depends on what application and which software you're most familiar with. And then, like I said before, where DFT methods are kind of a genre, basis sets are specific implementations of DFT or other quantum methods with certain assumptions and simplifications made. So when you select a basis set when you're doing a calculation, you want to know what assumptions are made to tell you if that basis set and that method will work well for your specific application. So kind of going to what I do, I use DFT methods in SSNMR crystallography. And SSNMR stands for solid state nuclear magnetic resonance. And crystallography is just trying to get the crystal structures of different molecules. So every molecule in a certain phase will have a crystal structure when it's in one of its solid phases. And knowing that crystal structure can tell us really important things, like for biomedical applications, knowing the crystal structure will tell us how easily absorbed a drug will be by the body. So certain phases and crystal structures of drugs are more readily absorbed than others. And so my research is actually on a drug as well. It's on a drug called docetaxel. And docetaxel is a huge chemotherapy drug with billions of sales. And my research is on determining, basically proving that there is a previously undiscovered conformation of docetaxel that's in a new structure that hasn't been predicted yet. And so the research I do is I use CASTEP and other programs to calculate NMR parameters. And then I'm fitting the theoretical model that we built and we calculated NMR parameters for it to experimental data using these calculated parameters. So you can see in the graph on the right that there's a correlation, and those red lines are from about 5 or 6 other, or the red dots are from 5 or 6 other molecules that we have really good experimental data for. And we used that experimental data to build this correlation between experimental parameters and theoretical parameters. And as you can see, the R squared value is about 0.995. So we can predict with really high accuracy the experimental param or the theoretical parameters from the experimental parameters. And so if you look at the green dots on the graph, you'll notice there's a distinct outlier at about x equals 25 and y equals about 175. And that actually shows for one molecule where the docetaxel theoretical model does not agree with our experimental data. So we can use that and some other statistical methods to prove that the model of docetaxel we have or the experimental crystal that we've created data for isn't one of these structures that already exists. So I've gone through and proved that for all the existing structures. And this is especially useful for really difficult systems. So I'm sure you guys might have heard that for things like proteins or any kind of large molecule, it's really hard to get kind of accurate structural data on the molecule, and it's hard to calculate as well. And so using DFT with these methods is a really great solution for that problem. So these are just some bonus images of the molecule that I work on. So this tells you about the size. So docetaxel is pictured on the left, and then the supercell on the right is kind of a depiction of how crystal structure would look like. So it's a whole bunch of docetaxel molecules that are all next to each other, and there's intermolecular forces between the different molecules. And then on the right, that's just the traditional line structure of the docetaxel molecule. So you can see what it looks like. Okay, so other DFT research. There's a lot of amazing material science and computational and physics work that is done using DFT methods. So this is just a graphical abstract that I liked. It talks about catalyst preparation for a chemical reaction, and they were able to model how the catalysis functioned on a molecular level using DFT methods. And so there's a lot of amazing applications in material science and biomedicine and computational chemistry where we're able to understand reactions really from a base level of how the molecules are interacting. And that kind of understanding helps us design better reactions and design better catalysts and things like that. So on to the computational demands side. So generally DFT calculations scale with the cube of the number of electrons in a system. So the big O of time complexity is n to the e to the 3. And so you have to keep in mind as well that with each additional atom you add, depending on the size of the atom, you add a different amount of electrons. So heavier atoms, like metals or other things, but even organic atoms, each additional atom you're adding to the calculation will add another 10 to 50, electrons. And so quite a bit of complexity can be added quickly in these calculations. And that's why we need supercomputers to run them. So many different implementations and variations exist, but in practice, different steps of the calculation can be the rate limiting step, just depending on what types of things you're trying to calculate. And most of the software that I mentioned earlier, like Gaussian and CASTEP, take advantage of the hardware accelerations and the software optimizations that we've talked about in this class. Like for example, CASTEP uses MPI to communicate across different nodes, and then it does parallelization within the node, as well as taking advantage of other optimizations like matrix math that we've talked about in this class. And there's two more things. So plane wave is a method that's used for periodic systems, and pseudo potential approximations can greatly simplify calculations by sacrificing some accuracy. And these methods basically just ignore all the electrons that are not valence electrons in a molecule. So yeah, that's the simplest way of putting it. And they just make the calculations a lot faster. So the general trade-off between speed and accuracy kind of continues. That as methods become more accurate, they tend to be slower, and the ones that make more approximations tend to be faster. So basis at precision, the computation time often increases by orders of magnitude. So often for a small increase in precision, your computational time might double, or quadruple, or 10x. In practice, most calculations are done with a basis set that has the best balance between enough precision and also manageable computational time. And I will say in recent years, methodology improvements generally haven't kept up with the advances in compute technology. So computers and the resources available, like GPUs and other hardware accelerators, and just much faster compute, has increased faster than methodology improvements have increased. And so there's still some gaps to be made up by the software providers to fully utilize all the new advances and take the most advantage of them in calculations. And so I wanted to finish my presentation with kind of an interesting case study, maybe a little bit more interesting than my research, about what you can do with DFT modeling. So I looked around and I saw this paper that I really liked. And so this group used DFT methods to model the molecular docking of SARS-CoV-2 spike protein with different antiviral compounds. And so this is obviously super relevant because antiviral compounds are an important treatment methodology for viruses and especially new outbreaks. And so they wanted to see how these different antiviral variations performed against COVID without having to actually perform the tests physically to verify. And this holds a lot of potential in the future for being able to design rapidly antiviral medicines without needing to basically guess and check, which is what they do currently and what they've done so far. And so the molecules were created digitally, and then they were optimized using DFT methods. So the optimization just ensures that the structure is at an energy minimum. And then after optimization, DFT methods were used to find the HOMO and the LUMO, which is the, as you can see in the image, kind of, there's these little clouds. And the HOMO and the LUMO are just the highest occupied molecular orbital and lowest unoccupied molecular orbital. And those indicate the most likely place that the antiviral molecule will bind with the protein. And they use that information to predict potential binding sites. So where on the protein will this antiviral compound bond? And then this theoretical information was used to predict the binding of the 4 antiviral molecules to the spike protein. The researchers also collected experimental data to confirm that the predictions made with the computational work was correct. And in this case, it was correct. And they were able to predict the potential of any given antiviral molecule to combat COVID in this case. So it was a really interesting case study, and it's just one example of the amazing potentials of this technology in different fields of research. So thank you all for watching my presentation and for your attention. I look forward to seeing all of your presentations and wish you all luck.